So let's kick this off. Good morning. Hello. I bring a ducky to every single talk that I do because that screech at the beginning lets me get everyone's attention. Because I know in between the breaks and stuff like that, people are still finding their seats. So for anyone still wanting to join the talk, you guys can find your seats, and the ducky helps you find where to go. Also, rubber duckies are fantastic because they're cheaper than therapists. And I'm from Switzerland, so they can get pretty pricey pretty quickly. Another added benefit is that during conference talks, there tend to be demos, and we tend to plead for help to the demo gods. And I'm not going to risk that. That's why I keep a rubber ducky very close with me. In case something goes wrong with me today, we're going to take our friend over here, squeak it a couple times, and see if we can come to a solution. But today's talk is going to be about solving real-world data fetching challenges with Next.js and TanStack Query. And I like to call this a pragmatic case study, and we'll see why in a second. I also like to start this talk with an interesting fact. Now, in 2006, Amazon did a study, and that was a long time ago, but Amazon did a study on a page load and how it affects their ARR. And ARR is your annual recurring revenue. And so an increase in 100 milliseconds in your page load time, they found actually reduces your ARR by 1%. For them in 2006, that was $107 million a year. Today, that would be $3.8 billion. Now, for Amazon at a large scale, that 1% makes a difference. If you're working on a little demo app or weather app and you're charging for that, maybe the 1% doesn't make a difference. But in certain instances, page load really makes a difference. I also like to set the stage in my talks because everything has its own context. And so the patterns we're going to be looking at today, and yes, we're going to be looking at architectural patterns, there is no one-size-fits-all solution for them. So we all have our unique project requirements and environments. We're also going to be talking about a couple of key technologies. And I believe that the documentation for these open source libraries and frameworks are absolutely fantastic. So today is not going to be a tutorial learning those technologies. I also like to make my talks framework and library agnostic. So a lot of what we're going to be talking about is applicable to many different frameworks and libraries that you could use. And then there's a big thing called premature optimization. And as engineers, sometimes we love it when we can get the performance numbers looking absolutely beautiful, make the most performant function possible, render a page as fast as possible. And I like to talk a little bit about a story around premature optimization. I was once consulting for a startup in New York. And so they were telling me a little bit about their engineering setup. And in their engineering setup, they were telling me that they had this DevOps engineer that was building this beautiful Datadog dashboard. Beautiful observability dashboard so that if there was any issue with the platform whatsoever, you could figure it out in minutes. And so they were paying this guy probably $300,000 a year, you know, those New Yorker salaries. And when I asked the question, how many users do you have? The answer was 0. And so somebody was spending their entire day building a dashboard that wasn't expecting to have any logs anytime soon. And it's not that users were coming the next day. It was no time soon before even finding product market fit or anything like that. And so we have to be careful and pragmatic sometimes to choose when do we want to optimize something and when it's okay to leave alone. Well, what's the problem statement for today? The problem statement is, what challenges do developers face in creating a seamless user experience due to complex data fetching, something we quite commonly do in web applications, and then managing that data once it's in the web application. But I also like to rephrase this in, how can we build optimal solutions in suboptimal conditions? Because we seldom find ourselves in optimal conditions. So when you have struggles like your backend team not being able to prepare endpoints for you, or designs not being ready and you have to work with mocks and things like that, those are things, especially in the startup world, you find yourself being in very often. Things are seldom perfect, so we've got to get creative. The question you may also ask is, why bother with all these performance improvements? Why bother going for the creative solutions? And if we're talking specifically about page speeds and things loading, becoming interactive for a user, 0 to 2 seconds so happens to be the golden window for that, where you get the highest conversion on a web page. And this is specifically for user-facing web pages, not necessarily internal dashboards and stuff like that. Those are things where you can let go a little bit. And to dig into it a little bit, there are these 3 important limits when it comes to response times and things that you visually see on a web page. And this is an extract from a usability engineering book, and you can find that online. Now, those 3 limits start at 0.1 seconds. This is usually when a system feels like it's reacting instantaneously. It feels really snappy, really nice. Then when we go to 1 second, that's generally the limit for users' flow of thought. If you want to have a very seamless flow and going through an application, clicking through a bunch of things, anything taking longer of a second starts to get in the way of that. And then 10 seconds generally seems to be the limit for keeping the user's attention. I would think also this, these days with the amount of attention deficit we may have due to, the content that we consume, 10 seconds is already being generous there. When it gets to bounce rate, so somebody going on your web page and then leaving, if your web page loads within 1 to 3 seconds, it's around about 32%. Moving that all the way to 10 seconds can be up to 123%. That's no small jump. Now, I like to talk about another thing, which is this magical number that we may have heard in the past, specifically 14 kilobytes. No particular answers, but has anyone heard 14 kilobytes being interesting in terms of networking and payloads before? Or are we introducing this for the first time? Okay, first time. So what's interesting is that we may have heard that 14 kilobytes fits within a single initial congestion window of a network request, which means it minimizes round trips to a server. And I have a little bit of a drawing to kind of explain what this means. So if you look over here, your computer or whatever your client is wants to request a website from the server, request some information, some data from the server. If it's under 14 kilobytes, it's just going to return the whole thing. And then it's going to say, thank you, everything's rendered, we're very happy about that. So that's what we're doing. We're trying to fit some information into the initial congestion window so the server doesn't need to actually send an acknowledgement. This initial congestion window is essentially how much data can be passed before an acknowledgement is required, before you have to go for a round trip and be like, increase the congestion window, bring me the rest of the information that you have. And so if we were in the scenario of a website being 15 kilobytes, what it would look like is, can I see the website? Here's the first 14 kilobytes. That's not enough. So can I see the rest? And let's go back and let's fetch the final 1 kilobyte. And then we're happy and we can render everything. And that's just not just for your initial HTML. That's for any type of network requests, TCP connections being made. And what's really interesting about this is that when this 14 kilobyte rule applies, actually just having an increase of 14 to a 15 kilobyte payload in some instances increased the time for the response to be resolved by 600-ish milliseconds, whereas the difference between 15 and 16 kilobytes was absolutely negligible. Now, these days, that rule is a little bit obsolete. So that applied more in the time of HTTP 1 and something like that. And these days, the principle does still apply, but we don't have to always fit everything into 14 kilobytes. Actually, in some instances with modern CDNs like Cloudflare, you can have an initial congestion window up to 46 kilobytes. And so you can push for a lot higher. But again, this is really dependent on your setup. What we were talking about was in that round trip, in that I get the 14 kilobytes and I have to request the next bit. That's called the stall. And your stall cost, you can calculate it by understanding what is the round trip time. What is the round trip time for a singular request? And this round trip time is really user dependent because one of the variables is the network bandwidth or the type of network that your user is using. So in a LAN situation, which is generally the best, it's 1 to 5 seconds for that cost. And so it's barely noticeable. When it comes to typical broadband, you're maybe looking at 30 to 70 milliseconds. But then if we're building global applications, especially mobile-first applications, they'll be on 4G, 5G networks, and even certain situations, 3G networks that still exist. And then things at 80 to 200 milliseconds might start to get noticeable. So instead of focusing on those 14 kilobytes, well, that's a conversation starter, the general rule of thumb actually should be get your critical rendering payload under the initial congestion window. And it's interesting to figure out what does that initial congestion window look like for your setup and your users. And we can get pretty creative with that, and we'll see how. And if we look at a platform like Twitter or X, when you open that, it's a client-side facing app, it's a single-page application, client-side facing. A lot of network requests are made for your image assets, CSS, JavaScript, all those sort of chunks, and there are easily over 100 requests being made. And when it comes to what of those requests are critical not to make up your page, actually fitting within this initial congestion window can make quite a big of a difference. So we alluded to a little bit of the technologies that we're going to speak about today, but I'm going to dig into it ever so slightly more. There's Next.js, not Nuxt. That is the React framework. If React is the library, then Next.js is the framework. It's a little bit more opinionated than just using React in of itself. Anyone here use Next.js, just for context? All right, so we've got the right crowd with us today. Cool, so it allows all that cool stuff like, server-side running, static page generation. There are a lot of things built out of the box, like routing. You don't need the React router or TanStack router. So there's a lot of stuff built out of the box, but I won't go too much into it. And the next thing is TanStack Query. Has anyone used TanStack Query before? In a previous world, this was called React Query. That's where it started out at, but it migrated over to TanStack Query so that it's a little bit more framework agnostic, so you don't just get fixed into using it with React. You can actually use it in the Vue world or in any other framework and library. And I really like to focus on the wording of this. It's a powerful asynchronous state management library. A lot of people, a lot of developers that use TanStack Query think that it's just a data fetching library. And it just so happens to be really good at data fetching, but it's built as a global state management library, and it's just good at anything that's asynchronous. So you can get really creative with it. And it's generally not the right idea to be able to query something from TanStack Query and then throw it into your use states. It's actually meant to be used as a global state management solution. So that means you can do a lot more than just data fetching with it. The next thing I want to talk about is API types. And this is not an exhaustive list. But earlier on, Daniel was showing us a bunch of public APIs that we could use. And one of those APIs didn't work. So we've got public APIs. One of the examples of those is not the Cats one, but the Star Wars API. That's one I've liked to use. There's also a Pokemon one. And what's interesting about the public API type? It's a black box. You have no control over it. You have no idea if it's working or not. You have no idea if they do any level of versioning. You have no idea about the performance, about the rate limiting, and maybe if it's well documented, maybe it's not. Maybe just somebody wants to cut the server cost down and shut it down one day. So when you think about the API types that you work with, you have to think how to make use of the API in terms of what strategies you want to apply when consuming the information from it. So when it's a public API and you don't have control, you may have to employ some resilience patterns, or you may have to employ some backup strategies to ensure that your application does not break because it's consuming something you don't have a lot of control over. Another type of API are internal APIs. Internal APIs is when you've got a product team at a company, and you've got your front-end team that's building something, and you've got your back-end team that's building an API. And the front-end team is using an internal API that the back-end team is building for the front-end. And why this is so nice and flexible is you don't even have to abide by having any open API specs. You don't have to abide by a lot of rules. You don't have to abide by semantic versioning. If you just want a new endpoint, they'll create a new endpoint. The backend team will do that. If you just want to switch around how the keys look like, change the JSON structure, it's not a big deal. All you have to do is update the consumers, which may be your mobile application or your front end, and you're having a great day. Then there's a category I like to call partner or product APIs. And these are APIs that are sold as a product or designed for third-party consumers. And the scenario we're going to look into today is a little bit of a problem that I faced a couple of years ago when I was working at an API-first company, where the front end that we were building was consuming an API that so happened to also be sold as a third-party product, which means that I can't go to the backend team and say, hey, I need this new endpoint. Hey, I need you to give me this kind of data. I need you to do this. These query parameters don't work for us. And things get a little bit difficult because even if they were to make changes to those APIs, you have to follow deprecation policies. You have to inform all of the consumers, their costs associated with it. And so things start to get complicated. And so the APIs that you work with have different pros and different cons. And so I implore you to actually take a little bit of time and all the APIs you interact with, whether it's Stripe for payments or Pokemon APIs, think about the limits and the pros of working with that particular endpoint and how you may have to adapt the way you're consuming it based on those limitations. Now, let's put our tech lead hat on, and let's say we get a Jira ticket, and we're dealing with one of these types of APIs. So what we have now is our front-end team needs to design a dashboard chart that displays the distribution of birthdays for the top 5,000 users in the system. And this is the situation that I faced a couple of years ago. Not with birthdays, but it was a financial dashboard. And so we were dealing with a partner API in the sense that we built an in-house API that was being consumed by third parties, by other people who were selling it as a product, which means that I can't go to my backend team and say, hey, I want this, I want that. And that's the limitation. So what's highlighted in yellow here is key information that as a tech lead, we put our hat on and we're starting to think of stuff. OK, I need to have a chart now in my front end. OK, there are 5,000 users that I need information for. Whenever we get a Jira ticket or whenever we get a technical interview that we're doing a system design interview, there are limitations. You're getting constraints and information to work with. So what's the constraint? So first, before we get to the constraint, the data is available via an API, which returns a list of users with all the data. Check mark, fantastic. I can get information from somewhere. But that limitation is that the backend is unable to provide a new endpoint or a data warehouse, which is what would be more ideal from a chart-based scenario, that returns the data format that we need from the front end, and there's a limit of 1,000 users returned for each request. And I could not go to the backend team and say, hey, can you increase that to 5,000? Because there were some limits in terms of the database response time and things like that. We wouldn't meet SLAs for customers. So there's a limit there. So we put our tech lead hat on, and we've got to draw an architectural diagram. And where do we start in building this front-end system? So if we look at this architectural diagram, we've got a user interface that we've got to build. We've got to build that chart interface. And we've got a singular request that returns 1,000 users. So you may think, I got to make 5 requests now. So to be a little bit smart and not do them sequentially, you're going to make 5 parallel requests. Cool. That's got its own set of problems with that, but that's what we're doing. To have an interactive user interface, what you're going to first do is set a loading state. You're not just going to have a blank screen. And there are 2 things that can happen. You can have an unhappy path. Something goes wrong. There are 5 requests. There are 5 points of failure here. And then when you go down the unhappy path, you may choose to persist the loading state. So something's going wrong. Maybe we're trying to recover from it. And with any typical resilience pattern you may put in place, the most basic one is a retry. So let's say we throw together a custom retry function, and we just retry the request when something fails, either all of them as a group or the individual ones that failed. So you can choose one of those 2 strategies. That's one thing. Then there's the happy path. The happy path is the loading state resolves. I can now receive the data from all of those 5 requests, and now I've got to map it. So I've got to convert it into something that's usable. I'm going to then set it into state and render my UI. Now, what can be a problem in React, if you're using React, is that you tend to create a very basic fetching function using a use effect. And a use effect essentially will rerun depending on the dependencies that it has. So depending on the way you structure your components, your React application, you may land yourself in a scenario where one state update so happens to affect a dependency in your use effect array and then causes a refetch. And when that refetch happens, you may be refetching data that you don't necessarily need to refetch. So we may land ourselves in a place where state updates that are unrelated in our application end up risking us getting a 429 error, which is too many requests. So that's unideal. State management starts to get complex. So if we look at how this hook may be created, let's say we call it use fetch data. In there, we're getting all this data from a Faker API for our birthdays. The quantity is 5, so it's going to make those 5 parallel requests. Passing through an abort signal in case the component unmounts and we want to abort the requests. And then we get that data back, and we're going to put it through some mapping efforts. So we're going to get the birthdays by month, and then we're going to map and create this chart data. We're going to set it into state. That's what we're going to do. So let's have a look at a demo and see what this initial version of our application looks like. That kind of tries to solve the Jira tickets requirements. So worked with some UI UX designers to create this beautiful UI, and we're going to have a look and see how long it takes to load. That was not too bad. If we go into the network requests, we're going to open it up, and we're going to see what happens when we try to load this data. So I'm going to hide and show, and then we're making 5 parallel requests as we agreed to. And so seeing it's taking some time for all of those to load, and each of them have a fairly large size. If we go into the payload, what we actually see is we're getting information such as their address, their phone number, their profile picture. We're getting a lot of dense information in there. But you so happen to also see that in the chart, we're not making use of any of that information. The reason I have this hide and show button there is to show you how sometimes unrelated state updates can actually negatively impact your data fetching, because this hide and show button is entirely, it's related to only showing the component or not. But is it really necessary to refetch the data every time we hide and show it? I don't think somebody's birthdays will have changed in that time, nor will we have that many users. So there's something clearly wrong going on here. If you are really good at math, you will have calculated that all those requests put up together are 2.3 megabytes. That's no small payload for all of those 5 requests. And 73% of that is unused data. So let's think a little bit about the key factors. So we had a custom retry function, and a couple of the problems with that is that if we're reinventing the wheel, and there are a lot of NPM libraries that do that, having it internally means you need testing, maintenance, it's subject to bugs. In terms of caching, there's none by default. That's why every time you're hiding and showing, there's some refetching going on. It's unnecessary. The data's not stale yet. State management can get complex. Of course, I've put this example together to show that, but some complex React apps that I've seen actually have a really hard time, especially when using context providers, to manage state really well. And so it's hard to manage it globally, especially. Locally, it's not too bad. And then handle that data staleness. When is the data stale? How long can I keep it around before it's irrelevant? And then when it comes to data mapping, we're doing that effort on the client. And what you'll see very typically in React applications is that you'll use a bunch of use memos and use callbacks to do this memoization effort, and it's not always necessary. But it's a very typical thing that's done, and a lot of linters recommend it. And I have an entire set of opinions on that I'm not going to get into today. And in terms of the payload, it's not optimized for state, nor is it actually optimized for caching. Because when you think about local storage, actually it has limits. Browsers have around about a limit of 3, 4, maybe even sometimes 5 megabytes when it comes to local storage. Those are not the only requests that you're making multiple other requests. You can start running out of your local storage memory allocation. That's where the backend-for-frontend pattern, your best friend forever, comes into play. And there are multiple variants of this architectural pattern. The one that we're going to be looking at today is called the transformation bridge, or the aggregation proxy. And so that alludes a little bit to what it's trying to do. It's trying to aggregate some data, and it's acting as a middle layer. It's acting as a proxy. And why it's really cool is you get to have it adapt to platform requirements. So even though we have an internal API that we're selling to other people, and we can't change it much, let's say there are 3 clients, a TV client, a mobile client, and a web client that need to create this chart data. So you can create one BFF service, and then you can serve multiple internal clients. That's really useful. Then you also decouple your concerns a little bit, so the front end's also not in charge of all that data mapping effort, all the managing of multiple requests that you're doing in parallel. And then the other great thing is you can start optimizing a lot more for performance, whereas you're not dealing with a lot of side effects. You just have that one BFF proxy and service managing however it's going to do the data mapping and whatever data structure and whatever method so happens to be the most performant to do that. So what happens is that we take this large structure we decided to receive for every single user, and now we condense it into the minimum viable information we need to actually render the chart data. So what does this new architecture look like? So we're still starting with our user interface, but this time we're making one API request, and we're making an API request to a Next.js API handler. And what's nice with Next.js is it's really easy to create these API handlers, these serverless functions, these functions. And it's not exclusive to Next.js. There are a lot of other frameworks that let you do that. And it doesn't actually have to be a Next.js API handler. It can be a microservice, not even having to be written in JavaScript. It could be written in Go, whatever you want it to be written in. There's just something in the middle that's doing some work. Make that request, same loading state. Now that proxy is what's handling the 5 requests. So we still have to make those 5 requests. That's a non-negotiable. The API hasn't changed. Now we can enter our unhappy scenario. We get a failure. We return some error code. And we still have our custom retry logic here that's trying to retry everything. But what's nice here is that we have just one point of failure for the client, and the server is now having to handle the multiple requests. When it comes to the happy path, we're going to map the data on the server, so the server is responsible for that. Then we're sending the data to the client. We set the state, we render the UI. And then we land at that same state management scenario where a React state change happens, make those requests to the API handler, even though it's one request. Then that makes, in the proxy, 5 requests, and we end up having a 429 potentially. So when we look at that hook that we created a little bit some time ago, how does that change when it comes to the BFF? You're just going to, instead of doing all that effort on the client, you're going to make that request to that service, pass the quantity, and whatever the payload is, that's what you set into state. So it's not too much different. You're just changing how you're fetching, where you're fetching from, and you're not doing any effort on the client. So none of that use memo stuff, none of that use callback stuff, no memoization effort needed. So what are the key factors that we had a little bit of a conversation about? Failure isolations. We isolate to a single client request rather than managing multiple. Makes it much easier for you. I just care that I failed to get the chart data. I don't care about all the little requests that make that up, potentially. You have a much easier time managing your code base with a clearer separation of concerns. All of that data mapping is happening at the proxy level, so you don't have to do all of that memoization effort on the front end. And then now, the payload can be optimized, as we said, to the minimum viable values, which means that if we're going to start implementing caching later on, you're going to be caching a much smaller subset of the information than previously. And this is also easier to manage in state. Now, if we look at a second demo, how we've evolved this architecture, we're going to go and we're going to load the same thing. Wasn't that a lot faster? We're still making those 5 requests under the hood, and we're not caching anything. We're subject to that same issue when I hide and show, we refetch things, but now we're just receiving the bare bones chart data. How many birthdays for what month? That's all that I care about. And if you're very fast at reading, you'll see that that's 666 bytes. It's a 99.9% payload reduction. Now, I'm not saying if you go and implement a proxy and all of your services, you're going to have a 99% improvement in every single piece of data that you're fetching. But this goes to show that if you're now able to reduce certain payloads down to below what your initial congestion window is, you can start getting a little creative with improving the performance. So when we're talking about network bandwidth, that's a big variable when it comes to your users. Not everyone is developing on local host, LAN cable, and you're having a great time because you've got 200 or 300 megabits per second for your network connection. When it comes to that 2.3 megabyte payload, how long does it actually take to download on a Wi-Fi connection, which is around about 90 megabits per second? Around 210 milliseconds. Of course, there are a lot of variables involved in that, but call the pure download speed based on megabits per second 210. That's all right. Not all of our users are on Wi-Fi. If it's a mobile application, 25 megabits is not too bad on 4G, but then also you have data roaming and all that sort of stuff to take into consideration. Your download time goes to 740 milliseconds. We're still in one of those limits of under a second, so we're still able to keep the user's flow of thought, but that starts to get a little bit higher and noticeable. Then when we go to 3G connections, that download time shoots up to 9.2 seconds. And that gets problematic really fast. So when it comes to that 660 bytes, it's very easy to guess. But on a Wi-Fi connection, less than a millisecond when it comes to pure download time. When it comes to 4G, you're still under a millisecond. And when it comes to 3G, you're still under 10 milliseconds. So even though our bandwidth has gotten progressively worse, we're limiting really how bad it takes, how long it takes to download that information, and that makes a really big impact. And when it comes to deploying your API handlers or whatever your microservice is, there's an interesting thing called ingress versus egress. Has anyone heard of ingress and egress before? Okay, 2, 3 people, wonderful. So ingress is the amount of data coming into a system or network. And typically when you're deploying, let's say, to Cloudflare, ingress tends to be free. Egress is what's charged. Egress is data coming out of a system or network. So all these cloud providers are very happy for the data to go in, and then they're going to charge you when you want to get it back out. But that becomes interesting because when we're fetching those 5 requests, that's the bulk of the data that's ingress. But then egress so happens to only be those 666 bytes. From a cost perspective, it starts to get interesting. Then you have your 2 options, which is your function as a service or infrastructure as a service when in terms of deploying a backend-for-frontend or a proxy. And so your function as a service, which tends to have an average lower ingress bandwidth. It's very hard to calculate ingress bandwidth. It's very cloud provider dependent. But that's your AWS Lambdas, your Vercel Edge functions, and your Cloudflare workers. And one of the little penalties with that is that you have cold start times, which means that those functions as a service aren't always hot and ready. That has a small performance impact. So there is a cost of moving things over to the proxy. So at a certain scale or a certain amount of requests, it starts to make sense, but not always. But function as a service tends to be cheap. Then you have your infrastructure as a service, tends to have much higher ingress bandwidth, and those are your AWS EC2s, your GCP computes, and Azure VMs. And those are always running, may incur a slightly higher cost, there's no cold start penalty, and so on and so forth. So we've talked a little bit about the BFF, and now we're going to talk a little bit about TanStack Query. And so the documentation is absolutely wonderful, but what's so great about TanStack Query is that it handles a lot of this stuff that's going to help us solve a couple of these problems in terms of handling caching automatically, in-memory caching, and then you can also have some plugins for offline caching. Auto refetching, data staleness management, all the global state management that was really complex, does a lot of stuff for us. You can have dependent queries in the sense of when I maybe add a user to the system, then I invalidate the chart data and I fetch it again, rather than assuming that maybe a user is added every single hour. So there's a lot of dependencies you can start to tie together when it comes to TanStack Query. And so let's involve TanStack Query in this architectural diagram and see how it evolves. Now we're still making that one API request to the Next.js handler. This time it's React Query that's being involved in that request, so it's managing it. We have a loading state. Instead of this being a loading state that we control, in a use effect, you may start the loading at the beginning, make the fetch, and then set the loading defaults. We control the story. And now with React Query, it handles the loading state. So you don't have to worry about the state management here. Still making the 5 parallel requests. Unhappy path gets hit. And then you fail return error code. And now React Query handles the attempts to retry. And you can set a limit 3 or 10 or whatever it is. You don't have to manage any of that. And what's really cool is you can now configure some things out of the box, not just basic retries, but retries with exponential backoffs and jitters, which fix thundering herd problems. And so when it comes to exponential backoff, instead of retrying immediately, what you do is you wait a second, then for the second request, maybe you wait 2 seconds, 3 seconds, you give some breathing space. Let's say we get to the happy path, we map the data on the server side, we send the data to the client, and we cache it in memory. React Query derives the state from the response, we render the UI, and if any state change happens, TanStack Query is going to be like, hey, do I have something in the cache? Is it still valid? Let me get that. If it's not valid, then we start the journey again. So we start to reduce our risk of that 429 error. And so the function doesn't look too different. Instead, now we're using this use query over here. We're passing some query keys that help us cache and manage the reference to that cache, setting a stale time, how long the data is considered stale for, and we're passing over that same fetch request. So what are the key factors here? Third-party library is now handling loading, errors, and deriving the response state. So we don't have to do any testing in this library. It's been battle tested before. That's fantastic. Caching. We've optimized the optimized payload can now be cached, and we can use multiple caching strategies. So that's great. We can do offline cache. We can even use something called local forage, which then decides, depending on the browser, whether to use IndexedDB, WebSQL, or decides to use local storage. So that's a really cool option. You can plug that in. In terms of re-renders, you limit the refetches, and you manage data staleness. And you can also manage garbage collection. So for how much time is your component unmounted, will TanStack Query still retain that cache? And then there's resilience out of the box. So when it comes to operating with providers or operating with APIs that you don't know how they're going to react, things might fail, you can configure all those retries, exponential backups, and so many more patterns. But let's get creative, and we can go one step further with this. And I'd like to talk a little bit about query criticality. And we took that example of, on an X or Twitter timeline page, there's those 100+ requests that are being made. I don't believe every API request carries the same importance. And so if you look at these two API requests, auth profile, fetching your authentication information, maybe there are groups and scopes that come associated with that are really important to know if you're authenticated and authorized to use the application, and the chart birthday data. If we were to think which request is more critical to the application, I would say it's the auth profile one. And the reason for that being is that if I don't load my groups and scopes, I risk a security issue of my application by not having that data. But the chart birthday data, I can live without. And so let's look at a third demo. So we're changing things up a little bit, and we're going to actually start fetching things on the server, and we'll show how that looks in a second. And when I load this UI, you'll see no network requests are made on the client side. Hiding and showing things with TanStack Query, no more requests are being made. State is being managed real nicely. Over here, we've put a timeout. I've reduced the timeout from 2.5 seconds down to 500 milliseconds. And what this is doing in terms of resilience pattern is that what it's trying to attempt to pre-fetch the data on the server, dehydrate it and pass it along in the HTML, and then if it so happens to take a long time to resolve it on the server, because the problem with now moving a fetch request to the server is that if it takes too long to resolve, you send no HTML to the client. At least on the client side, you can render some other stuff and wait for the network request to resolve, but you have a blank page until that happens. The timeout hits, we bail the request on the server, and now we try to recover on the client, and that's the magic of query keys, because you can tell TanStack, hey, I tried doing this on the server, it didn't work out for me, so try to recover on the client. So yeah, that's what we're doing here. Now, the next thing is, Fariz, instead of jumping through all of those engineering hoops, couldn't the backend have just made the endpoint? Why did we have to go through all of this? Painful journey to evolve an architecture and jump through all these hoops and figure out how network requests work, caching things, throwing in these libraries, BFF patterns. It's not really the point. The point is, first of all, be pragmatic, because your backend's not always going to be ready for you. So sometimes you have to get creative. I've been in so many situations where Figma designs aren't ready for me. I have to deal with mock data. OpenAPI specs are half-baked. So you have to be pragmatic sometimes to move things forward. But also the joy that we have as engineers is that sometimes we can go down rabbit holes and be curious and figure out how can we take advantage of certain things around us to have some more optimal solutions, again, as we said, in suboptimal conditions. And then just be creative at the end of the day. It's not ideal sometimes to work around all of this stuff. The fun fact is actually this architecture stayed in place for 2 years. We were never able to make that endpoint for 2 years, so it was useful in this case. But it isn't always. So sometimes it's good to understand the limits of what you're working with, the positives of what you're working with, and see how you can come to the best of both worlds with the pros and cons. Thank you for your time. Any questions? I will assume then everything has been explained. All right, let's go. At the end of the day, the user doesn't care how long the network request takes. They care about something being interactive for them. So it'll always be more important to get whatever the real user time is for something. So you will have to calculate not only the network request time, but also the proxy computation time, and then the cold start time as a function as a service, and also the rendering time, because there are all those different components that lead up to a user actually being satisfied with an end result. So it's all of those pieces that you add together, and that's actually will lead to you understanding the real user satisfaction. And I think there are a lot of observability platforms. I think in Sentry you even are able to detect user frustration when they're rage-clicking buttons and things like that. There are signs through the web events that we can use to detect when things get frustrating for users. So combining those gives you a good idea on like how healthy this may be for conversion. Does that answer? Yeah. Yes. Yes. So caching on the backend side is an entire separate beast. And it's a lot more complex than on the client side. Because on the client side, I can just happen to refresh the user session, and then I can just wipe out the cache and deal with stuff like that. The backend at some point actually would have to choose to potentially cache the data per user. Because if the chart data is different per user, I have to now know what users has access to what and track that with every single cache. That's what gets complicated. But then there's also some endpoints that you don't care about, and you can just cache it for an hour or something like that. But the tracking of the segmentation of cache starts to get more complicated on the back end, and that I don't necessarily have a straightforward answer for. For TanStack Query, I think it's much easier to move some of that cache to the client. Hopefully not at the risk of overcomplicating your local storage management, because when it comes to managing cache in the local storage, there's user manipulation. So they can break the structure of the user of the local storage. You'll have to add validation in place, make sure you're clearly separating things. So there are a lot of other complexities that come with that, but it's generally much easier to manage on the client. Well, it ends up being whatever's easiest. If, like in the situation that I was dealing with, it was Java microservices being written by the backend, and the backend had zero capacity. So the frontend had to be empowered to write that API handler, and so JavaScript, TypeScript was going to be the easiest solution there. I generally don't recommend for something as simple as this that you deploy an entire JavaScript microservice or an infrastructure service, because then if you're dealing in a microservices world, you have to deal with adhering also to the engineering practices the backend team does, and there's a whole, you have to fit with the whole deployment infrastructure around it. In terms of having it with Next.js, however you're deploying it, whether you're deploying it to Netlify Vercel, you already have the capability to quickly launch one of those API handlers. So in terms of having a frictionless developer experience, I recommend just putting it in the place where it's easiest for the front-end development team to work on. The whole limitation here was the back-end team didn't have the capacity. So that's why you have to get creative on the front-end side. Yes. Yes. So what's nice about the proxy server is that we're hitting it less because the front end is caching. So the amount of times we're making those requests again, it's much less. Because on the front end, let's say you want to cache for an hour, there'll be an hour in between requests just for a singular user. So the amount we're hitting that API, is much less. But yes, if you were to hit that proxy the same amount without the front-end caching, you would land yourself in the exact same problem. So in that case, it would be more creative to put caching on the proxy level. So again, every architecture is unique, and it may be easier to manage on the front end, but there is a limit at which it is more reasonable to put the caching at the proxy level. And that's specifically the case if you want multiple clients, because if you're actually servicing a mobile client, a TV client, and a web client, you want to then not maybe have to repeat the same client-side caching strategy across all three. So then you may want to centralize the caching. But then, of course, you have to deal with the user state issue. Any other questions? Well, that's my time. Thank you.